In terms of remodeling approaches, it depends on time scales and what's important and what isn't, as always, right? So there's just simple one-way coupling where you set a pore pressure field and then that effective stress adjusts how the constitutive models behave. And this is for very high permeability or very low loading speed, where the water has a lot of time to adjust to the mechanical response. So things are pretty much one way. On the other extreme, there's undrained behavior, where pore pressure develops due to deformation of the soil. So the soil squeezes and that generates pore pressures, but the pore pressures don't have time to go anywhere because the time scale of the fluid motion is much higher than the time scale of the mechanical system, right? So this is all kind of one-way coupling the other way. And then this is for very low permeability or very high loading speed. A lot of dynamic analysis, in fact, almost all dynamic analysis are in this regime where you're doing something very fast to a fluid-filled system, but the fluid doesn't have time to go anywhere because the time scales for that are too high. So that's a fully undrained analysis. And there are examples of that in the manual and we'll show. And then there's fully coupled, where things are, time scales are close enough to each other that you have to take care of both at the same time, one way or the other. This is where life can get computationally expensive. Okay, you gotta do a fluid calculation and a mechanical calculation at the same time, make sure those two things remain compatible. So this, how do you, what do you do within FLAC2D? What are your options? And this is a sort of a list of options, and you'll see the arrow goes, your life gets more and more complex working with FLAC2D as you go down this table, right? So first, there's no flow calculation. You just assign a pore pressure distribution. You say, I've been given a water table by the mine or by the site people, and I'm just going to assign those pore pressures and leave them alone and do a fully mechanical analysis, assuming those pore pressures. This is very common. You don't even, in this case, there's no fluid flow going on at all. You never even have to configure fluid. You don't modify the mechanical. You just set a pore pressure table and let it use the effective stress. Then the other one is you don't know what the flow field is. You don't have a site examination. You don't have somebody else giving you the water table. You know what your boundary conditions are, and you have some approximation of things like permeability. So you do that calculation yourself. You set the boundary conditions and you solve the system to get what the pore pressure field is. Again, this might be steady state or transient. It might be that all you're interested in is the steady state field, or it might be that you need to do excavations in material, for example, and then do a between this excavation and this excavation is going to be 2 weeks. I need to know what's going to happen to a fluid field in those 2 weeks. Sometimes you just care about steady state. Sometimes those time scales are important. Now, the next level is that you actually care about pore pressure generated by mechanical deformation. So now you're doing two-way coupling. But this is an important thing, right? And then the next generation is that everything is coupled together, both ways. And if the time scale is important for both, then you have to do what we call a loosely coupled analysis. And I'll show an example of that. That can be very time consuming right now. So let's look at the first option, no flow. All you're doing is you're assigning pore pressures in your model. That's it. And then those pore pressures are used to modify total stress into effective stress before it goes to the constitutive model. So what procedure is you set the pore pressure everywhere in the model. You don't config fluid. You don't change. You don't add any calculation or memory to the system. You just use one of the options we give you to set pore pressure. Those options in your version of the code right now are you can set a water table. In this case, you can set a very simple water table with the zone water plane, meaning I've just got a plane in space. Pore pressure increases below it due to gravity. You can actually use, and this is very common, an imported or geometry set you create, a geometric description of what that pore pressure table is, that water table is. And it will automatically look at that surface and calculate pore pressures below it and set everything to 0 above it. Or you can just initialize the pore pressure. A lot of times you just got a simple linear field and you can just initialize it with a gradient through gravity yourself. It's important to note that when I said you don't have to config fluid, whether you config fluid or not is important for a couple things. But one of them is that density, solid density, the material density is treated differently in FLAC2D depending on whether you config fluid or not. Okay. And you should keep this in mind, because if you don't config fluid and you're just setting pore pressures, then material density is material density, it's not changed. And if it's important to have the water included in the material density, you have to do that yourself. So you have to manually change the density below the phreatic surface if that's the thing that's important. If it's not, you can just use density as density. But as far as the mechanical logic is concerned, it's using whatever density you set. And if you need to modify it for water, you have to do that yourself, okay? Config fluid, then FLAC2D is automatically gonna calculate the adjustment to density due to the fluid, right? Given the fluid density and the porosity of the material. And it'll adjust wet density automatically. But it won't do that unless you config fluid. So for this option, all we're doing is setting a pore pressure field and we're not config fluid. If you need to adjust density below the water table, you have to do it yourself. Again, the method for setting pore pressures, and these are actually examples, you can set an initialize, you can just initialize it. In this case, you're initializing it with this gradient where this is basically rho G, this is gravity times fluid density. You can specify it as a plane and then just everything below that plane as you go down. Okay. And then this is really the most common thing nowadays is you import water 01 as a geometric set that you've imported previously. So you've got some surface that somebody else gave you, and now you just use that surface. Say this is my water surface, and below that pore pressure is generated. Again, using gravity and the fluid density, which must be specified beforehand for that to work.